The other stress that they apply is what is called as electrical stress. That means VDD. Okay. It may be that VDD is supposed to be 2 volts. Okay. If VDD is 2 volts, increase the voltage to 5 to 10% above. So, maybe increase it to 2.1 volts, 2.2 volts, and decrease also. So, decrease it to maybe 1.9 volts and 1.8 volts. So, when you reduce the voltage, the delays will go up. When you increase the voltage, stress mechanisms will set in. So, typically voltage stress is actually this, increasing the voltage, that kicks in a lot of failure mechanisms. Okay. So, sometimes they will do it in a range. See, they will say we will go from 1.9 volts to 2.2 volts. So, they will apply all voltages between 1.9 to 2.2, and they may do it only for a sample of devices. Even for burn-in, see, burn-in also, it may be very expensive to do burn-in test and voltage test, okay, stress test. So, these are expensive tests. So, it may be difficult to do it for all chips, difficult to do them for all our manufactured chips. So, therefore, you may want to sample devices and apply to a sample, and then try to use some sort of a intelligence, right, to decide whether other devices have the same problem. Okay. So, that is what I was referring to. If you are finding that VBox, this is also called as VBox testing. If, let us say, you realize that in a certain area the VBox is failing or something like that, so maybe you can use AI or something like that to identify those chips which are likely to fail based on the data that you have. Okay. So, these are all highly data science things. Okay. So, data science plays a major role in all this, because every chip is different, right? If you take a wafer, there are wafer imperfections in the chip, there are impurities in the wafer, then the polishing of the wafer may not be uniform, the thickness of the oxide may not be uniform across the chip. So, there is a lot of variation and lot of measurements may have to be taken, right, and great amount of data science is involved in sort of deciding whether a chip has an infant mortality problem or not, what is the life cycle of a particular chip, right. So, or the lifetime of a particular chip. So, there is a certain amount of data science that is used. It is highly data science intensive. So, when they apply these tests, etc., they may first apply at the wafer level itself. It is called wafer sorting. Some simple tests are performed at the wafer level, maybe continuity test. See, what if the VDD itself is not connected correctly to the circuit, right? It is not going to function, it is dead. The clock may not be connected, ground is not connected. So, these are all really bad things that have happened, right? So, it may be fairly easy to identify those during in the wafer itself without having to package them. See, after the wafer is manufactured, you will do what is called as dicing, right? That means you will take a diamond thing, cutter, and you will cut all the silicon chips, and then the small chips will be packaged, and these are the ones which are sold. Okay, this costs a lot of money, right? This packaging and assembly, right? This is called packaging and assembly. That is very expensive. So you don't want to do this for all bad chips which are like without VDD, supply is not connected, ground is not connected, some inputs are not at all connected, right? So I have made this chip, right? That input is open, output is open, it's all wire is cut, something like that. So wafer sorting is a way of some people call it wafer probing. Okay, so the reason is I think they have a probe with the test electronics, and that will sort of make contact with the pins on the wafer directly and apply these tests, and they will mark the chips which are bad. So this is called inking the wafer, and when the pattern comes out, that there may be a certain pattern in the failures, right? That pattern also tells you something about what could be the manufacturing defect. Okay, so that is also another place where data science plays a role. Okay, you may be able to look at the data pattern of the failures, right? See, suppose if something like this is happening, right? All these are bad. So maybe you can decide that there is a scratch or something like that. The wafer may have a scratch. So you can figure out certain things about what may have gone wrong by looking at the this failure patterns. Okay, they call these as shmoo plots. So shmoo plots means a plot which shows which wafer is bad, etc. So it sort of that connectivity of these X marks, okay, that may lead you to conclude something about what may be going wrong in the manufacturing. So this is an important thing, because using data science we may be able to identify what is causing the problem. See, one thing is to improve the quality of testing and supply good chips to the customers and supply reliable chips to the customers, but it's equally important to learn something from what is going wrong. Why are these chips failing? What is in the manufacturing process which is causing them to fail, so that you can apply a corrective action. Okay. So reliability plays a major role, especially in the modern new applications that are coming up, like automotive electronics, industrial electronics, biomedical electronics, etc. So, you may hear a lot about reliability if you join a company which sells electronics to such industries. Okay. So, what if this chip is actually bad? Okay. So, we have sold, can we guarantee that the chips are good? That means quality is good, and can we guarantee their lifetime? If you have to do extensive reliability tests and extensive quality tests, right? Meaning you have to do lot of different kinds of fault models. Okay? And here you have to do lot of different kinds of stress tests, etc. So, all this will cost you a lot of money, right? Not all customers are willing to pay that kind of money. Okay? And even if you are, let us say you do have a customer who is willing to pay a very high price for high quality, high reliability chips, so you can never ever make a statement that this chip has no fault, right, or this chip will survive for 5 years. It's very difficult to make such a statement because our testing is never going to be 100%. We have considered certain fault models, but have those fault models looked at all failure mechanisms? May not be. We have considered certain failure mechanisms, but there may be failure mechanisms that are not covered. For example, how did we go from stuck at faults to bit faults? There was a time when we were not doing bit fault testing at all. The reason why they were forced to do bit fault testing was because they started observing that this kind of short circuits are beginning to happen because we are moving to more we are scaling the technology. So, as a result, producing the masks, etc., exactly the way you want, reproducing the features exactly the way you want, will be very difficult. So, bridge faults had to be introduced, and then later you introduce transition delay faults because of all these via that I talked about, high resistance vias and things like that. Okay. So, as we discover more problems, new fault models have to be introduced. So, when we sell a chip, there is always that chance that it will fail within its lifetime, right? Or it may not be a bad chip to start with. It may be a bad chip to start with. So, what do customers do in that case, right? How do they, if I was, let us say, a vendor of automotive, right? I am a company that makes electric vehicles and so on, right? I want high quality, high reliability chips for my electronics because my customers are important to me. I am selling these cars, and if there is an incident of some kind, then I am liable, right? And we know that chips can possibly fail, right? So, that is a safety problem. So, chips may fail. See, remember this bathtub curve? See, even here there is a small chance of failure, right? So, if you are making many cars, right, then definitely some of them will have those difficulties. So, if a chip does have this problem, then the designer must try and find ways to still make the the product safe. Okay, so design the car or whatever electronics that you are designing, design the product for safety, meaning even if there is a failure, the product can tolerate or can degrade in a graceful way. Okay. See, for example, if the car engine has developed that electronics that control the engine has developed a problem, at least maybe it is a, if it is a self driven car, then it should try and find a safe place and figure out what is a good way to park the vehicle somewhere safe, right? If it's an elevator, okay, and let us say the electronics fails between two floors, then can it at least go to the nearest floor and open the door so that nobody is trapped inside? Okay, can it go to a safe state? Can it go to a safe state? So, this safety is a big consideration. Okay, you will hear a lot of people talking about safety if they are working on electronics that is related to these things like biomedical, automotive, industrial electronics. In all of these kind of situations, if some failure occurs, at least we should go to a safe state so that the damage is minimized. So, there are some standards on this. So, standards exist, and people who are involved in design and test of chips for these markets must adhere to those standards. Okay. So, these are some people will refer to it as functional safety. That means when the chip is functioning, if there is a problem, it should still go to a safe state. And there are many levels of safety. Okay. See, some may be very, it's not a big deal if some small error occurs. See, for example, if the infotainment system in the car develops a small issue, it may not be such a big deal. Okay. Whereas if the engine control develops a problem, it's a very big deal. Okay. So, there are many levels of safety. Okay, these are called levels, safety levels. Okay, so we have discussed two important points, reliability and safety, and how stress testing can be used to assess reliability, and how things like Shmoo plots and data from the fabs can be used to learn about what could be wrong and fix the issues. And we have talked about functional safety. It is, if failures do occur, the electronics will fail. Okay, either it was already bad when we bought it, or over a period of time it has aged and it will fail, right? In that case, the system should go into a safe state. Okay, so we'll continue from where we left off. So we sort of more or less completed digital testing. So we'll next consider memory testing and also analog testing. Okay, all right.